And this mechanisms happens when we have two or more vacancies. And here I just wanted to quickly show you the range of lithium migration barrier that we can see, in which in general the ODH mechanism has lower energy barrier.
Good. Okay, great. Thanks, Zanab.
Yeah, that was good. Go 1 minute. So
Great.
I'll say my comment. Overall, it's really good. It's a really good topic. It's a hot area these days, lithium battery and stuff. Can you go slide 2?
Yeah, sure.
My impression from this, you explained it really nice, and you explained the two different mechanism. My only thing is that you have a lot of text in this figure. I mean, this slide. I think you explained it like, and you mentioned the two mechanism, and you can just maybe have the bolded text like right there, but you don't really need the definitions because you talked because I kind of had a hard time like either listening to you or reading the definition itself.
Okay.
And
Thank
I think
you.
that's all, but the rest is pretty good. And yeah, that's all.
Thank you.
Good, thanks. So Zainab, one thing I think is that, just thinking about this is like, you want to solve the problem of like, I'm out and my battery dies, right? And so we all can relate to that, right? And so maybe an image of somebody, in the, somehow conveying that idea is saying, how do we make batteries last longer, right? That's something that we can all relate to.
Okay, I see.
So
okay.
Setting up the problem in a way, again, it's trying to bring it down to something that your audience can really identify with. And then they're like, oh yeah, how do we do that? And I think that would be helpful in the first slide. Again, I would put in an image like that and just say, say it in words. The second thing I would say is that here we spent a fair amount of time on this this different thing about the movement of the lithium, but I'm still unclear on what's the new thing. I mean, what are you doing that's trying to change the? Are you're saying that most people use the dumbbell hop, and your idea is to use the tetral site hop?
So basically, this is just a background to actually like explain how a lithium can move, like the different movements.
Okay.
Yeah.
Because what I would say is like something to give us intuition of like, well, everybody's doing this, but I'm doing this.
Oh,
right?
okay.
Because you said, well, at least because you said this is my research, so I was kind of
Yeah.
tuned into like, what's the new thing that she's doing, right?
Oh, I see.
And so leaving that up, and here on this slide, I would say, probably, and I don't think this exists, but it would be possible maybe to construct it, but having a little animation would really help, because the motion, it took a while for me to see what was going on, but if you had a little loop of it doing it, then I would get an idea. But then I still want to know why. Like, is it because of that shorter term, the shorter motion is more energy efficient or something like that?
Okay.
But it made me interested because I agree. I think this is a very hot topic. The one thing I've heard about, which I don't know much about, but it's that there's all these algorithms for how you charge up the cells and that there's a lot of it's huge. It makes a huge difference even with the same hardware. If you use a different algorithm, you can actually make the charging faster, and that the battery lasts longer. So all kinds of interesting things around batteries. So thank you. And then the last one is the last slide. Okay, so here you're getting at this idea that there's certain materials that may end up giving us much better performance. Is that the key idea?
Yeah.
Okay, good.
Can I add something here?
Yeah, sure.
Yes.
I love the talk. I worked with cathode materials in the past. I feel like my main comments would be, so in the first slide, you talk about why it's important to study lithium diffusion, but it's just like a tiny little sentence. But something that can be like a huge attention grabber is that like when lithium diffusion gets really, really high, I mean, back in the day when lithium ion batteries when there were lithium ion battery or lithium based batteries in cars, there was a huge car explosion that like led to some I forget which company that was responsible for it, that in the end they found out what was happening was there was a lot of lithium diffusion that like created these like dendrites that ended up penetrating the battery material and then exploded. I think that would be a really good like start to show the significance of the topic. And another thing for like the daily usage, adding on to what Professor Goldberg said, with lithium diffusion, it's sort of what makes lithium ion batteries like not as reversible. So every time you realize after a while your device, you sort of charge it and then the battery doesn't last as long as it was when it was a new battery. And showing maybe one of those like Rankin plots where like the capacity of your battery decreases every time there's a cycle.
Oh, right.
Would sort
Yeah.
of drive that home, because lithium basically, once it diffuses, it doesn't really go back, and it makes the like active material not lithiated, and then it doesn't really get charged anymore.
Okay. Salim, that's good. Salim, let's
Thank you so
not
much.
go into too much detail on the specifics.
Yeah, just
Okay.
those two concepts. Yeah.
Got
Thank
it.
you.
Okay, good. Let's go on. Let's go on to Claire now. Okay.
Hello, my name is Claire, and I'm going to talk about the electrolyte that's used in electrochemical devices and the harsh conditions that it endures. And these devices, to give some background, can consist of many different forms and are made of many different materials, but ultimately they're a stacked system layered with lots of different parts that perform the function of either of many different things. But for one example, there's a fuel cell, which takes in hydrogen gas and reacts at a catalyst layer, moves that proton over and reacts again, which that whole reaction process allows you to power some device with electricity. And the end result is water. And an analogous device does the exact opposite, takes in water and makes hydrogen using electricity. My focus is the electrolyte here, which undergoes a really harsh environment. And they are really important for the performance of these devices. Their importance comes from their function, which transports that proton, as I mentioned, which is important for their actual creating electricity or hydrogen gas. They prevent electrons from transferring, so they act as an insulator from electrons, and they prevent gas crossover, which could be dangerous for the user and undesirable for the reactions. One type of these solid polymers electrolytes are this PFSA, which has a certain structure based on the chemistry that allows it to function. So there's this hydrophilic end group, which attracts water, and a hydrophobic backbone here, which gives it strong structure and mechanical stability. And these opposing forces relate to the overall structure of the material. So they form these nanodomains of hydrophilic end groups that really attract water, creating these water domains, and thus the pathways for the hydrogen protons to transfer, and that polymer matrix, as I mentioned, providing stability. However, because of the harsh environment, they undergo a lot of stresses from swelling of that water and from the constraint of the assembly. And then from that high stress situation that they're enduring and the chemical environment, very acidic, hydrogen gas and oxygen, pinholes can form, delamination can occur, different types of cracks. And so that can be a real problem for the end user. And that's all I've prepared today. Thank you.
Okay, thank you, Claire. Good. Okay, let's go back to your first slide, if you will. And Zainab, do you want to give her a couple comments?
Sure, yeah. So I like the figures. It was very clean figures, and the explanations, I think it was clear. I could follow it easily, although I was not like super familiar with this topic, but it was very clear. And yeah, I think in general it was a good talk. Yeah.
Thank you. How was I on time? I don't know if I didn't hear anything. I saw some comments in the chat. But
Yeah, no, it went a little long, Claire, and we didn't.
Okay.
I don't think Zainab had her timer. Was
Oh,
using the timer.
Okay.
I thought I had to only give feedback. I didn't time her. Sorry.
Oh, okay. No worries.
Sorry
no
about
worries.
that.
No problem. But here's the thing. I think one question I have, I'm reading this again, this title, and I'm still, how would you characterize this title I mean, can you say it in another way? What's your message?
That the polymer or the solid electrolyte undergoes harsh conditions, I think
But when you say harsh condition, I mean, I guess what I'm trying to get at is you're saying that that these devices degrade in practice. Is that what you're saying?
So, okay. So my research is on like the mechanical stability of the electrolyte. I didn't dive into all of my research, but the reason for that is that they undergo damage during their lifetime. So we want them to survive for 10 or plus years without service.
Okay.
And
so
depending
where do you see electrolytes? Where are they used?
Yeah, so these electrolytes that are in, say, a fuel cell, they can be used in cars or other devices, like small portable electrolytes, fuel cells, that anything that needs power can be used with those. And then electrolyzers, those are more larger, like stationary type places that are actually creating making hydrogen gas.
Okay, so that was one thing I think would help Claire, is that just maybe some picture of a car and the plant, because electrolyte, you know, I kind of know that word as a term of, you know, that there's electrolytes, say in what is it, what do you drink, that drink?
Gatorade.
Gatorade, thank you. Yeah, that's what I think of when I hear electrolyte. So I wasn't sure where we're going here. And electrochemical devices, I don't really know what you mean. This is a case where I think, you know, this is and I'm not picking on you, but I think it's really helpful for everybody. But sort of know your audience and then step back away from your specialty, because one of the things that we often do is we're so close to the topic, right? It's your research after all. You know this like the back of your hand. It's obvious to you, but for us, we actually don't know what these things are. So this picture actually didn't help me, because I look at this picture, I see, it's actually partly it's because it's very grainy, but I don't understand it. And so, you know, I didn't know if something's going into a house and there's an airplane. You see my point? It's not,
yeah.
it doesn't convey. So I think it's saying, I'm interested in, there's a new thing, there's a very effective way of generating energy, which is using hydrogen and electrolyte, and that's called an electrolyte. And that is going to be, there's these new kind of cars or these little mini plants that do that. But the question is, how do we make them last over 10 years, right? And that's the fundamental question. Now I'm with you. And then you start to.
I didn't want to ask that question because I wasn't prepared to answer it.
Okay. Well, no, but you could say, but that's actually, by the way, I want to also emphasize that's a really effective thing, a rhetorical question, which is, how do we make this last for 10 years? Now, you can perfectly say, and your audience will actually like this if you say, I don't know the answer, but this is what I really want to solve. Okay. And when you admit a little bit that, you know, I gave a talk once when I said, I've been studying this problem for 35 years and I've made very little progress. And I just saw my whole audience just like lit up. They loved to hear that. And then I was going to tell them about the progress we did make, but it was really helpful because they had a sense of, you know, I'm not going to just sell them something. You know, I was now, you know, they were with me. Do you see what I'm saying? So you can ask that question and you can say, we haven't figured this out yet, but that's why I'm in grad school. And so, you know, I'm here to solve this hard problem. Okay. And I also think that, you know, again, for everyone's benefit, the meta lesson is audience. Know your audience. And I would say so important is the talk that you'll give, even with the same slides, to the people in your lab is so different than the talk you'll give to like this class versus the talk you give to the public, right? Or to a high school group, right? Those are going to be, you're going to talk about the same thing, but in a very different way. So always try and think about who is that audience member, where are they coming from, what's going to engage them, because generally they're not going to know even if they're in your field, they may not know all the terminology. Okay, good. All right.
Thank you.
Excellent. Thank you. Thank you, Claire. And let's go on. We got Isaac and Robin, and then Clara, and then Shunan. And I think that might take us up to the end. So Isaac, so Claire, you're going to time Isaac here. 50 seconds. Isaac, you about ready to pull it, show up your screen?
Yeah, I'm just sharing my screen. Okay.
Maybe we'll get to Enze. I think we might go all the way to Enze because I see that he's the last one with his hand up. Who's the brave volunteers of today? We'll get him. We'll get us all in. Okay. So Isaac, yes.
Okay.
Can you your see 50 seconds of fame? Go ahead.
Great. So hello, I'm Isaac, and I'm going to talk how to estimate treatment effects. So suppose that we want to estimate the effect of a policy. In this case, what is the effect of Proposition 99, which is a tax increase in tobacco and cigarettes? So from this graph, we aren't very sure what is exactly the effect of this Proposition 99. So the idea is that we are going to implement this to estimate this counterfactual. What would have happened if California didn't pass a Proposition 99 based on other pool states that actually don't have this treatment effect, this treatment, sorry. So our key assumption is that we are going to be able to estimate synthetic California based on certain ways that we're going to be solving from this optimization problem. So what we have is, now that we have constructed a synthetic California, we can see that actually we have a deviation from our synthetic California and the actual California, and we can estimate the difference to be the effect of this policy. So now the problem is, how do we conduct inference in this methodology? And we can see in the right panel that there are many several methods that try to construct confidence interval for this methodology. And what I did is the blue dotted line, and as you can see, it's better in the sense that it has narrow confidence intervals. So that was.
Okay, good. All right, thanks, Isaac. Claire, any comments for him?
Yeah, I thought your slides were really nice. I liked the design and it was really consistent throughout. I think you could reformat your figures a little bit to be ready for a slide like this, because the text is a bit small and sometimes the focus gets a little lost. But I think the example and bringing it into the real world of like the effect of cigarettes and like these like the treatment effects, I think that's really nice.
Good. Okay. Thank you, Claire. And Isaac, so I saw something in chat about using Beamer. Is that what you used to do this?
Yeah.
What's an open source?
Yeah, it's kind of like another package for LaTeX. So it's actually just like a wrapper for making presentations in LaTeX.
Okay, good. So can you do it on like Overleaf or something? Does that work too?
Yeah.
Okay.
Instead of in your first line, instead of saying begin article, or I don't remember the exact command.
No, that's okay. We
begin Beamer.
Begin Beamer. Okay, good. So here's the thing. I think it was really good. The cool thing is you have such a good topic there, but I would say start with a slide of someone, there's these vivid things of someone, someone's lungs on cigarettes, right? That we want to stop people from smoking, right? So if you look up stop smoking and search under Google, I'm sure you'll have no shortage of great images there. But pull out something, because that's really what you're about, right? So the question is, in 1999, California tried a technique to stop people from smoking, right? They imposed a tax. And you want to tell us that little bit of history, maybe with an image or a headline again, to indicate what that was. So now the question is, did that make a difference or not, right? That's what you're trying to, that's your big headline. And now you could say, what if we just look at, California did go down, but maybe that wasn't due to the tax, right? That's the other part of it. So the question is, can we have a model for California that would show us, well, what was how much of this was really due to the tax versus other effects, right? And you're correlating with lots of other states. Mm-hmm. They went down too. right? A big fact that's really affected the cigarette is the banning of cigarettes indoors, right? And restaurants. That had a huge decline in restaurant and in cigarette usage. But but that wasn't about the tax. So how much of it was due to the tax, right? So basically the bigger question is, how do you assign the causality, right, to a specific effect? So that's a really interesting thing. And then you say, now there's a mathematical technique out there. And unfortunately, the interesting thing is when you start showing the formula, right, of this linear equation, you've kind of, it's hard because it's hard to visualize it, right?
Yeah.
So one thing I would recommend in this case is if you could do that in 2 dimensions, you could actually tell your story really well. So just imagine you have 2 axes, two variables, right? And just make that summation over 2. And then you would be able to actually probably give an illustration of what those elements mean. And then say, this extends to n dimensions, right? That's a really effective way for everybody, by the way, when you try to explain something that's complex, project it onto a plane, because the plane is very nice. People can see what's going on. You can highlight what's going on, and then they can say, okay, I get that this can now go into 3, 4, 5, 10 dimensions, right? So keep that in mind. And I would just say at the very end, I thought it was really going well. That last plot, I thought was your closer, because you said, you had the plot where you showed the definition from the artificial California to the true California. You see a real effect, and that is due. So the answer is, because you want to close that loop, the answer is yes, that tax increase did affect the usage of cigarettes, right? And that's a really good closing point because it sort of wrapped it all up. But then you went on to another slide that sort of started something else about those gaps and things, and I could not follow what was going on there.
Yeah.
That was very complicated. So in other words, rather than take us on an arc that you open a big question, you kind of solve it, but then don't open another big question that we don't have time to go into. So
Yeah, that's true. Yeah.
You know what I'm saying? So here again, it's a matter of choice. It's a matter of selection and filtering, because for everyone, 60 seconds is not a lot of time. So you've got to pick and choose. And if you want to leave on a good note, you want to leave that really clear landing point where you can end and everybody's like, huh, cool, I got something new. You see what I mean?
Yeah.
Okay.
Yeah, thanks.
Okay, good. All right. Clara is up next. And so Isaac, you're going to time her. Clara?
Yes, hello. 1 second. I am just entering present mode. So I think I might have done it. I think I interpreted the assignment slightly differently. And I did a presentation like based on like what I would maybe like teach students.
Oh, that's fine. No.
Oh, yeah. So that's what it's about. Okay, so let me share. I hope it works. I have some animations, but I hope it works okay. Can you guys see it okay?
Yeah, we see a screen, but no movement on it. Should it be animated?
Oh, no, not yet.
Okay.
Let's see. Well, at least I think not yet. Hang on.
There is a way of sharing your screen where you can optimize for video. Do you know about that?
No.
Okay.
But that is good to know.
Yeah, if you unshare your screen, when you start to share, there's this tiny little button at the bottom. By the way, everybody should know about this. Okay, so unshare your screen for a sec.
Okay. Why can't I do
And you can also optimize for so when you share, click the share button. You see how it shows you which of those windows you have open? See, look at the lower bottom. There's 2 little check boxes. Do you see them? Optimize for. Click on both of those. So you're optimizing for audio and for video or something like that.
Okay, cool.
And everybody should know about this, by the way, because when you're giving talks, it will make everything work very nicely. And your video will come out much cleaner too.
Okay. Awesome. So then let me go over here. It's optimized. Oh, I guess you have to do like an authorization. Wait. No, it kicked me off. 1 second.
Kicked you out?
Let me go back. It stopped sharing for some reason.
Okay.
But hopefully.
I don't think.
Okay. No. Oh no, it's go. Oh, hang on. No. That's okay.
Take your time. You know, it's interesting. I was I shared this tweet today of yesterday. I think it was someone had shown a dog frantically digging around, and it was like, this is me right before my talk trying to sort through 2 million emails to find the Zoom link for my
It's
talk.
like I had it all set, and then it didn't work. Okay, I think it's gonna work now.
Okay.
That's my hope. Okay, so hi, so I'm Clara, and my research is in thermal hydraulics for nuclear reactors. So I basically study how heat moves. I'll give a brief intro into the 3 modes of heat transfer using a diagram. So here's an image that we will keep in mind as I define these modes. It's a pot filled with water over a fire, so nothing special. So let's go into some definitions. There's conduction. So conduction is the transfer of heat by direct contact between 2 substances. There's convection, which is the movement of heat by motion of fluids. And then there's radiation, which is the energy transfer with help from electromagnetic waves. So it's only 1 minute. So next time, what we'll do is we'll label where each mode is happening on this diagram. So I encourage you all to think to yourself about where you think each sort of heat transfer mode could be happening on this picture and come ready with some ideas. So that's all.
Oh, and you gave us the answer, right?
I gave you the answer. In the end, I was like, do I have time for this? And then I was like, I don't think I'm going to have time for it. So I just got it.
Actually,
Okay.
you was just in time. So I also didn't want to interrupt for the 50-second time mark.
Oh no,
but it
that's
was
totally
excellent.
fine.
Yeah.
Thank you.
Yeah. Good. Okay, that was great, Clara. And I think what you showed is that you could actually take, you know, one idea, but you could convey that in 60 seconds, right? That you didn't try and stretch it too far. And I think you, of everybody today, you know, had a really nice focused idea, right? It was just 3 different words, 3 concepts, and with a picture, and you know, that all held together. And that's accessible, as you were saying. I mean, that's not accessible to almost everybody. I mean, even high school kids could digest it. Good. And I thought the image is very clear. I think the one thing I might have done was say, try to figure out, you know, labeling those 3 things, 1, 2, and 3, and say, match those up, and then say, okay, then you show it and say, did you guess right?
Okay.
So that people would have a chance to, you know what I mean? So then they would have a chance to think it through, because you're right. One of the things, and this is, by the way, something that rarely happens in talks, but really effective, especially for teaching, is where you leave a question open. Mm-hmm. And you ask your audience again, what do you think? And you really will, that's a huge win, by the way. And you can do this in a professional talk too. People really like it because it's rare. Usually people are like, I did this and then I did this and I did this and I did this, and you're like, you know. But if someone says, and then what do you think I should have done here? Right. Everybody's like, what? And then you're like, and you're engaged. So when you use something as a question, that's perfectly fine. You're letting people think. And then, you know, and timing that is tricky, especially in 60 seconds. But if you sort of said, what do you think? And then leave it out there. And then, you know, maybe 5 seconds. And then now I'm going to show you the answer. And boom, were you right or not? And that is really great. So, you know, and people love it when they were right, by the way. They're happy to know that. But or when they're surprised, people will like that too. They'll say, oh, you know, I thought just the opposite, but no, you know, here's what it turned out. And you can think about this when you're presenting results too. And you can say, you know, I expected this to happen. And in fact, this is a very effective trick. You show a plot and you say, I expected this, and here's what we got. And you just wait that little moment. Everybody's like, and then boom, and it's like went up like this. And then, you know, then it's interesting, right? You've shared that you saw something surprising, so everybody is surprised with you. And that's what you want. You want to get people to this point of, oh, you know, this is not what I expected, right? That's interesting. And that's when they're going to start paying attention and remembering what you did. And again, if it's 60 talks in 60 minutes, how are you going to get yours to stand out, right? And that's the thing. And you'd be really surprised that usually that's what happens. There's like one or two talks that you're like, wow, that really caught my attention. And you look for that person later. And so, you know, and if it's a teaching a class, it's the same thing as like, how do we engage? Because again, students are tired, especially at this point in the semester. And how do you get them to sort of, you know, snap out of it?
Mm-hmm.
So, and I think but I liked your choice of subject. I thought it was so nice and clear and concise that you could do that in 60 seconds. And also the illustration was really, you know, compelling. Right?
Yeah.
It was really fun to look at.
Thank you.
Good. Okay, Clara. So, does anybody else? Okay, wait. We have who is next?
I think Robin was actually supposed to go before me. I don't know if we
oh, did we do that? Okay.
But...
Oh yeah. Okay. Sorry about that. That's right. Robin was before you. You're right. And then Sunan, and then Z. So Robin, you're up next. You ready to go? Okay.
And then should I time her?
Yes.
Okay.
All right. Can you guys see my screen?
Yes.
Awesome. Okay. Hello. I'm Robin, and this is going to be my 1-minute reason on why we use alpha particles for radiation therapy over other things. So radiation therapy, as you might know, is a method of cancer treatment. It's an alternative to surgery or chemotherapy. And the basic mechanism by which it works is that radiation has energy and it deposits and breaks DNA strands, and this kills the cells. The higher energy particles or radiation is more effective. But the problem is radiation doesn't really care if it's a cancer cell or a healthy cell. So the burden is on us to come up with a procedure that distinguishes between those two. Particle selection is one way that we can do this, and alpha particles solve both of these problems. So compared to alternatives, the figure on the left shows the energy deposition of alpha particles, and the two peaks are alpha particles and beta particles you can't even see on this plot. So they're on a whole nother level. Alpha particles also deposit their energy very locally, whereas beta particles kind of tend to wander off and might jump into healthy tissue. In a future minute, I can tell you about, no, that's all I have. In a future minute, I can tell you about the actual research that I do, but that's the motivation behind it.
Okay, good. Okay, great. So you're saying that, so most people are not using alpha particles, is that right?
So conventional and well-studied methods use beta particles, or they just use total body gamma radiation. And alpha particles have been demonstrated to be super effective, which is kind of this image shown here. You know, malignant tumors on the left, application of alpha particle therapy, boom, all gone. But what I'm working on is developing imaging methods, because this image is a cut image. And so we don't really have tools to look at alpha particle therapy in real time right now. You have to look at just like a before and an after picture.
Okay. Okay. Clara, do you want to add something first?
Yeah, so I liked all the images that you used. Like, I thought those were all pretty compelling. And it wasn't like your slides weren't messy at all, which I really appreciated. I kind of wish, so on one of your slides, you had things written in orange. And I almost wish it was written like bold, and like even just like the cancer cells does not equal, or like it can't tell between cancer cells and healthy cells. Like I almost wish it was like bold and just like bigger and redder, because it feels like that's really important for you. So I was like, I wish that would read more than even just like the radiation breaks DNA strands. Just because I don't know, I feel like that's like the idea I want to take away from this slide. But otherwise, I thought it was like a really nice topic to choose, and it's really interesting work. And I think your slides were done really well. That's awesome.
Great. Thank you. Thanks, Claire. I think here's the thing, Robin. If you go to the very first one, this one, I had no idea this was showing the result of radiation and killing tumors.
Okay.
Okay, I thought it was, I didn't realize that. Now I see it sort of as a figure of a person with their hands up. Is that right?
Yeah, Yeah.
See, I didn't even see that because I just saw something with speckles on it and something without, but I don't know. And I don't know what ACPSMA is. And do you know what I'm saying?
Yeah.
So here's a suggestion. I think your biggest point, if I'm understanding you correctly, is there's a new kind of radiation, or there's a special kind of radiation that can be very effective. And here's an example of how it can actually take out all of the tumors. This person has an incredible amount of tumors, and they've all been removed by alpha treatment. So let me tell you why alpha treatment is better than what everybody else is doing, right? So the thing I would do is just clean this up, and one trick, and you probably all know this, but you just make a white box, right? A white rectangle, and just put those white rectangles all over so you cover up all the stuff that you don't want to show, right? And just show those two before and after, and make it really clear that's a person on the left. And even probably the best thing to do would be to do it as two parts, so that you show this is a person with a lot of tumors, but with this particular new tech, I don't know if it's new again, but if a particular kind of radiation therapy, look how effective we can wipe all those tumors out, right? That's a really, now we're with you. Then the next slide, where you were going into this difference of, if you go to the next slide, see here, I think the key is there's two different things going on. One is that you're using alpha versus gamma and beta particles, but I didn't understand that here, because now we're talking about something else, which is just about radiation in general, right? And I think what you want to do is somehow convey the again, all radiation does this, but there's a way to I mean, maybe that is your point. Now I'm understanding a little better. Is that the whole thing is you want to target the cancer and not the healthy tissue, right?
Yeah.
And that's where
to target it effectively and actually be able to kill it.
You're right. And sort of like gamma is like hitting it with a sledgehammer, right? Something like that, right? It just hits everything and really strong. It doesn't make any distinctions. But alpha, because it's a weaker interaction, you can target it more effectively. Is that fair?
It's more like the range of alpha particles is very short. So you can attach an alpha emitter to cancer cells, and because they're only depositing in like a very small region around where they targeted, it's very likely that they're hitting cancer cells, not other cells.
Good. So I'm just thinking that you might think about an analogy there that might work, right? Like, typically what people are using is like coming out with a machine gun and they're shooting everything in sight, right? Versus what I have here is a very sharp knife, and I can just, locally cut things away that I want, right? I don't know, but I think it's something like that. Just think of that through of the visually that we'll walk away understanding that distinction between, the standard and what you're now researching. So that's just something I came up with quickly, but if you think of that analogy, that will really help. And by the way, it will help whenever you're talking about your work, whether you're standing in a line at a concert or something, just saying, hey, what do you do? And you say, I'm working on this new kind of radiation. And it's like, and then you make that analogy. Do you see my point?
Yeah.
Good.
That makes sense.
All right. Yeah. So excellent. Thank you, Robin. All right.
Very quick comment. Love the talk, super passionate about the topic. One thing I sort of just wish to see is the like typically if you're going to comparing alphas to like beta or gamma is not necessarily the best comparison. If you compare it to like proton therapy or like heavy ion therapy or like carbon therapy, it's more closer. It's more closer in terms of like the energy distribution and the deposition. So on that plot where you have the gammas, that like the beta is very low. Maybe if you added just protons and like carbon therapy as like the contenders to alpha therapy, although it's a little bit different.
Yeah, it would be more of like a comparison between current state-of-the-art research topics versus a comparison between alpha particle therapy and conventional.
Yeah, which is interesting because it's obviously such a such an important topic, and there's all kinds of therapies that are out there, and how complex it is to be able to actually make a difference there. But that's another thing you might do, is just sort of setting a little bit like there's all these new ideas out there. Here's one that's really showing promise, and put it in the context for us. Good.
And you're
Okay,
absolutely
good.
right, Salim. Those are super cool. And if I had more time, it would.
I know. That's the art of it. It's going to be, how do you do that in that short amount of time? And I'm just giving you tips for this. What we're doing right now is for that 60-second. You're in front of you're on these posters, and you got to quickly establish what is that really cool aspect of your own work, right? Okay, Shunan and then Enzi is going to wrap it up for today. So Shunan and Robin, would you time?
Yeah, I can do that.
Okay.
Hi. Yeah, hi guys. My research is about multi-arm bandits algorithm, and you can basically imagine this algorithm as an octopus with multiple arms, and it's allowed to pull one arm at a time. And its goal is to maximize the total rewards it gains from these bandits in a given amount of time. But the problem is it only knows partial information about the reward distribution of these, or it knows nothing about this reward distribution. So what it needs to do is it not only needs to exploit the best arm based on its current knowledge about these arms, but also it needs to explore new arms to gain more information about these arms. This is called exploration and exploitation dilemma, which is the key feature of this algorithm. And this algorithm has various applications on online recommendation or dynamic pricing problems.
Okay, good. Thanks, Shunan. Okay, so let's see. Who was it? Robin just now? Yeah. Go ahead, Robin.
Yeah, so first of all, I really like the cartoon as an introduction to really give like a flavor as to what you're looking at and kind of a visualization too for something that seems otherwise pretty abstract. You were super close to making the 1 minute, so I appreciated that you didn't try to launch into like another kind of question. The one comment that I think would have made it easier to follow for me is if you put maybe the applications at the start, or like use one of those applications to lead into what you're doing. I think that would have helped me contextualize what you're doing, because like the first thing I saw was this title, like multi-armed bandits, and I'm like, are we like Wild West out here? Like, what's a bandit? I wasn't totally sure where my head was at. But otherwise, like, really cool, and I want to learn more.
Yeah, that makes sense. Thank you.
I really like that piece of advice. That's great, because you're right. Start off with the why do we care, right? So that there's this interesting problem of how do I find a good movie to watch, right? That might be the classic question for a recommender system, right, Shunan? And or how do I recommend a product to a person who's at on my website? And so there's a technique out there this is called multi-arm bandits. Now, the one thing that you never defined was what a bandit is. And that's a crucial thing, which is the bandit is the name for a slot machine. Okay. So what you really want to start with is, I know this area pretty well. So I would have said, first define a bandit. You might just say, you walk into a casino and there's all these slot machines. Which slot machine should and I have a certain amount of money and I want to win as much as possible. So which slot machine should I play, right? That's the question. And the idea is, I have only a certain amount of time to be in there. I have a certain amount of money to spend, and I want to figure it out. So I start playing. I don't know which machine is better. So I'm going to start playing this machine and that machine. And as I'm playing the machines, I'm seeing when they get reward, which is the payout. Right. And that's what the idea is how do I pull these arms at in an optimal way? And that's the theory. Now, the other piece of this is that because multi-arm bandits in this case is a really beautiful piece of mathematics, you want to give this the source, the history. So I would maybe have said something like in 1955, I forget who it was, Thompson or somebody, basically figured out an elegant way of solving this problem, right? And so
Thomson
then,
sampling.
yeah, Thomson sampling. So you would suddenly now we learn about that this has been around since 1955, and he had this breakthrough that, you know, and it turns out we're using it all the time. So we used it in a paper that we presented today at noon on robotics, multi-arm bandits. It's a fantastic body of theory. And so really getting people excited about it. I worry a little bit about this image because it's kind of a silly and it doesn't really convey the power of what you're doing. Because first of all, it's not about octopus. And I don't see enough of the context to understand those machines. They don't, you know, I don't see them as slot machines. So if you do a search on multi-arm bandits in Google, I bet you will find some really powerful images of that. And then you say, I walk into a casino, here's, you know, I have all these slot machines to play, and which one do I do first, right? That's where you could convey that. Make sense?
Yeah, thank you.
Because again, what you're hearing, what we're doing in all cases, and you know, in all these cases is know your audience. Again, sitting back, what's going to bring them into? Why are they going to care? And if you start out by saying, what movie should I recommend? And here's the technique, and here's the casino. All of a sudden, these are things that everybody can relate to.
Yeah.
So that's what I want you guys to think about. Okay, great. Thank you, Shannon. So now we're up for Enzi. Last but not least, bringing us up to the 6 o'clock hour. Enzi.
Great. Yeah, hopefully this does not go over time.
Okay.
Can you all see my title slide?
Yes.
Yes, okay. Cool. Hi everyone, my name is Enzi and I'm super excited to share my research on superalloys. So first, what is a superalloy? Well, imagine you take a chunk of your favorite material and then you heat it up. Does this material get stronger or weaker? From experience, you might say the latter. But that's no fun. Superalloys are a remarkable class of structural materials that actually get stronger as the temperature increases, and they can retain this strength at very high temperatures. They are critical to the integrity and performance of airplane engines, power turbines, and nuclear power plants. Furthermore, these properties are strongly dependent on the chemistry. For example, if we add some titanium atoms into a superalloy, depending on where those titanium atoms go, it can greatly affect the strength of the superalloy. And so this leads us to our central question, and that is, how do extra alloying elements affect the strength of superalloys? Thanks.
Very nice. Okay. Shunan, do you want to make a few comments?
Yeah, I think it's a very interesting slides. Like at the first, like there is a wood there and there is heat there. And my comment is that if you can split the second slide to multiple slides, it might be better. Like for example, put the last photo to a new slide.
Yes, thank you. Yeah.
Good. Okay. Great. Thanks, Shunan. Yeah, Enzi, I really like it. Go to the first slide if you would. Yeah. Okay, good. So here's again where I would make use of your first. You put an image on this slide to get us, you know, some context of that, and maybe something to warm up whet our appetite on this topic because it's so visual. And I liked a lot that your language that you said, I'm super excited to talk to you about superalloys, right? And that was really, it was really good. So now we're really charged up here. You have your enthusiasm there, right? So then the next slide, and here, you know, this is interesting, but, you know, I guess what I would have wanted to say is like, somehow I wanted to see the contrast between the other things and the superalloys. So it would have been interesting to show, I don't know what, but like it would be ideal if you could say, here's like a structure made out of a regular material and it's all melted down after it's, you know, after it's heated. And then here's one out of a superalloy and it's still going strong, right? So side by side. Because when I just looked at this thing, I wasn't sure what I'm really looking at. It's sort of like, is this meant to be a piece of a turbine that's been damaged? Is that the idea?
I think it's just a turbine blade. chunk of a turbine blade.
But it's been damaged in some way, right? Because it's not a superalloy, or is it?
Yes, I guess it's perhaps not the best image. It's supposed to illustrate that turbine blades are made of superalloys. It's just
okay.
it's a single crystal, no defect superalloy, which is
okay. Okay, yeah, because I think we could just show that there's alloys and then there's superalloys, and so if we see them side by side, I get the sense of it. Now then, click one more time. This, I love that the image on the top. That really works. And I'm generally not a big fan of clip art in general. I find that sometimes it can be really silly and it kind of undermines, but this works really well, because does everybody see why he you could have showed images, but by showing it in this abstract way, it works really nicely. It's, you also have a really good aesthetic because the color, the way everything is kind of balanced. I mean, this is a really beautiful slide right here. Okay, it's got an art to it. Until next slide, bah, that threw off all your color tones and everything. Okay, I get it, it's effective, but I was loving everything about this so much, and I was like, oh, this is a work of art, until I got to this thing, right? So it's kind of like kind of a splash of cold water, right? Now it's not a problem, but it's also a little unclear of like what's going on, and I think that in some way what you're trying to get at is that by adding this titanium, is it, or what is the TI?
Yes, it is titanium.
Titanium. When you add titanium, that's what makes the difference. And so maybe some way, like there's an image out there that shows before and after the titanium, like little particles get in there that could really convey that, because that would be really helpful. And just also just keeping with the aesthetic of the slide, which is so strong. And then the last slide is, just put that up. Good. And you ended on a question. Okay. And and basically that's enough, right? For everybody, you basically said that you put out an interesting question and you said, that's what I'm studying. And that's really effective. Right. So everybody came along to sort of like understanding this is interesting, this is important. And that's the question I'm looking at. It's really interesting because in that scenario we're talking about, you have a very short time to present your poster, is that you've set it up, right? You've created the scenario where everybody's kind of interested, and you've now left it as a question. And that's like, okay, come see my slides, come see my talk, come see my poster, right? So it's a really good way to end. And creating that curiosity, the motivation is so important. That's going to also motivate your students, right? So I think that that's what we're getting at is motivation, is learning who your audience is, figuring out how to meet them so that you're gonna be engaged and want to meet you with what you're talking about. Okay, great. Thank you, Enzi. Really good.
Thanks for the feedback.
Absolutely. All right. So listen, this is really this has been great. Time flew by as always, and I won't see you for another week. So if you haven't presented, please take some of these ideas into heart, and hopefully you can polish your talk somewhat. And then we're going to do a few of them maybe next time, and then we'll do a breakout to make sure everybody gets a chance. And then we're going to be wrapping up. So have a great break, everybody. See you in 2 weeks. Bye.
Hey, Professor.
Yeah.
I think this might go better for next time since everyone's gone. But related to earlier, you were talking about keeping your audience, I guess, active. So I guess one of the things I've always wondered as a student in class, I haven't been a GSI yet, but how to, as a GSI or an instructor, how to get the class to answer more of your questions, or just to feel more, get them to raise their hands more, I guess. Because like sitting as a student, I see it more often than, I see more often that people are scared to ask questions than, like in this class, people really discuss a lot. So maybe suggestions that we could share next time.
Yeah, it's a hard question. I think this class has a really good, chemistry, and that there's a number of students who feel, are engaged. But there's also, I'm very aware, there's a good number, almost half that really aren't volunteering at all. And I don't know what to do. I've tried various tricks. One thing is saying, okay, for someone who hasn't spoken up yet, now, how about you? But sometimes students just don't want to do it. And one thing you have to be, that helps with is you can say, okay, I'm waiting to hear from someone who hasn't spoken yet, and just wait. And it's painful, but you could just sit there and wait. And everybody's like, finally, someone will step up. But, I think the best time to really get people engaged, and the best way is to really, when someone does speak up, make a fuss over them and make them feel good. Because that's the main thing, is that if you ever make someone feel bad for a question, that's going to have a repercussion for the rest of the semester. I can just tell you. And I've learned that by experience. I remember one time a student asked a question I had just answered, and then he asked a question, and I was like, were you here a minute ago? And the student was irritated. Students didn't ask questions for the rest of the semester, and I got terrible reviews about it. So I really learned, like, that one thing was really, really a huge mistake. So, that's the one thing, but it's a tricky thing. I have to say, I wish I had a better way to do it. And, but I'm always looking for ways, because I find that that's what makes it so much more fun for everybody. If people are talking.
Yeah, this is the first class I've been in a while where people talk this much. And I know it is more of it's a different style class than engineering, or like most engineering. So it's a nice change for sure, where it's normally silent.
Good, I appreciate that, Michael. And one thing is that when I think over COVID-19, it's a little bit easier to hang back, right? Because I know how that works. You just put it in, stop video, and then you're doing something else, right? That's harder to do it in a classroom. The professor has eye contact, and you can also point at people. It's really hard to do that here. So, yeah, I've actually been, that's another thing. I've been really pleasantly surprised. I have to say, this class has been incredibly enjoyable, and it seems like people are engaged. So, yeah, I really didn't know how it was going to go, but I am really pleased with that. So yeah, thanks for your question. It's a great one. Keep asking them. Go ahead, Salim.
I had a very quick question about the survey you talked about at the beginning of class.
Yeah.
Would it be possible to share the results from that survey? Because I don't know if you recall the outline that I sent you for the final paper. Maybe I can use, because I'm writing about teaching under COVID and the challenges under teaching under COVID. So if I can use some of the data from that survey in my final paper, that would be pretty cool.
Yeah, let me actually pull it up for you right now if I can find it. Just take me a minute here.
I wanted to distribute a survey myself, but honestly just haven't gotten to it.
No, it's okay. I should, this is my one, oh shoot, where did I put it? Okay, wait. Okay, wait. I think where I have the survey. Let me just see it. See if this is actually where it is. Okay, here's the survey, but where's the data? Okay, I'm not finding it, Salim. So let me dig around and look for it later. I have to do this after.
Okay, got it.
Yeah, if I can find it.
Got it. I can follow up by email if I don't hear from you as well.
Okay. Yeah, I'll see if I can dig it up.
Something else I emailed you about this, and I wanted to ask you, would it be possible to meet with you before Friday about the diversity statement, or?
Well, I mean, just what's the question? Because it's actually, my schedule is pretty tight.
Okay, I mean, we can also just save it for office hours on Monday if those are still happening.
No, it won't be in office hours, but just what's up? What's the question?
I mean, I just wanted to get your feedback on what is sort of appropriate to share and what is not appropriate, what is too personal to share. That's sort of my biggest challenge in those types of statements in general.
Well, I think why don't you submit what you have and what you think is best, and then let me give you feedback on that. Okay. Okay. I think that's the best way to do it. Yeah. I mean, it's really up to you and your comfort level. I don't think personally people, there's a downside to it. I think people generally really appreciate when you're more open, but it's up to you, that I don't want to push you. And I think, there are aspects you don't want to share. Nobody expects everybody to be totally transparent, but you want to share selectively with whatever you think is best. So I can't give you a guideline. It's not like I could say do it up to level 5 or something like that. It's just it's going to be.
I'll show it to you, and then maybe we can discuss what is sort of oversharing or what's not.
Yeah.
Any.
Okay. Sounds good.
Okay. I didn't really want that to be in the recording. I don't know if you can crop that out.
Professor.
Okay. Yeah. Okay.
Yes. Is the final report, will that be due during study week or during finals week?
During finals week. I think I put down there 9th of December for the final report.
Oh, December 9th. Okay.
Yeah. Sound good?
Yep. Thanks.
All right. Sure. All right. Thanks, you guys. See ya.